Now, normally at this point in the course we do a little practical where we give you a range of LEDs and we tell you the wavelength of them. So different colours of visible light. And we get you to measure the voltage that you apply to that LED. And we assume that that is equal to the energy of an electron that's decelerated through the LED. It's a bit like a backwards photoelectric effect, but it gives you the same relationship. You know the energy of your photons emitted by the LED because hc over lambda, and you know the kinetic energy, the voltage, of the electrons used to produce those photons. And you essentially go through and you use this data to plot a graph, and we can work out the work function of the metal within the LED, the energy required to, in this case, release a photon. You plot a graph with frequency on the x-axis and energy on the y-axis, and you'll find that it looks like this. It goes below and has a negative y-intercept, and the gradient is constant as well. Pause the video now and just have a little think. Given this equation, hf equals k plus phi, what is the gradient equal to on this graph? And how can I use this graph to find the work function? On this graph, you will have realised that the work function is the y-intercept, or rather, the y-intercept is negative work function. I need to put that much energy in. And the gradient of the graph is, of course, Planck's constant, h. Because if I rearrange the equation in this way, I can get a lovely straight line graph. E equals hf minus the work function. You might notice that there's a certain frequency above which it happens, and a certain frequency below which there's no emission. That is the threshold frequency, the frequency at which a photon is first emitted. It's lovely. I thought I'd just show it to you because it comes up on the end of topic questions, I believe, and I don't want you to be worried about it. Dead easy practical. If we were here doing it, it would be a breeze for you. Don't worry, you will have to do some of these practicals early next year or whenever it is that we come back. And this is a key practical that you need to know about. So here's an example of a bit of an off-the-wall question for you if you've not seen it on the photoelectric effect. It's a written question, probably worth up to 6 marks. It involves a little bit of knowledge of charge and a little bit of knowledge of the photoelectric effect and photons. I wish that I could do this demo in real life for you, because when I do it in lessons I'll show you and we talk through it and it makes sense. Here I'm just going to have to do my best. We've got this gold leaf, which is essentially just like aluminium foil, like a Kit Kat wrapper but made of gold. It's repelled from the main metal stem here. Why is it repelled? Ask yourself that. Well, it's because everything here is negatively charged, and light charges repel. We've got UV radiation coming in. It's asking to use the photoelectric effect to describe how the UV radiation interacts with the electrons of the zinc plate, and why, with visible light, no matter how intense and how bright, nothing happens. Well, again, remember what I said before. There's one thing that you should write at the start of every single photoelectric effect standard answer. You should know what that is. If you don't, watch that video again. So we start with that. An individual photon is absorbed by an individual electron. It's a 1-to-1 interaction. Write it down every time. Only photons with energy of the work function. So now we're starting to explain why it doesn't work with visible light. Only photons with energy above the work function of the metal will cause photoelectron emission. And we've added in here that that emission is instantaneous. It happens straight away. There's no time delay between, oh, we're going to absorb it, have a cup of coffee and then go. It just happens straight away because there's nowhere else for that energy to go. It has to continue to exist throughout that transmission. Just get in there that E equals HF. It's a basic fact, but it's worth a mark. Don't forget those easy things. The energy of visible light is less than UV. As a result, UV photons will cause photoelectron emission because UV photons have higher frequency and therefore higher energy than visible light, which has too low a frequency and therefore too low an energy to cause emission. So we've answered part of the question there. We're just going to add on that if there is any excess energy, the maximum kinetic energy of a photoelectron is the difference between the energy of the photon and the work function of the metal. It's the energy that's left over from that interaction. Now, this isn't really part of the question, but it's a really important thing to understand. Light is a wave. However, the wave model of light doesn't explain this. So I would like you to write this in somewhere where there's some blank space in your book. We won't go too far into the detail, but this is a key piece of evidence for the particulate model of light using photons. Turns out actually that both models are true depending on the situation that you look at. Don't worry about why, it's just the case, get over it. But in this case, this is evidence of light behaving as a particle. Just like Young's double slit is evidence of light behaving as a wave. Both theories are true. It's weird, but just get over it. You know, this is why physicists are great in those grey areas where there's no right or wrong answer. It's because actually both models are valid. Both models explain what's going on in different situations. There isn't an empirical truth. There is a model that works in both situations. There are some additions to this standard answer, so some additional questions. How does increasing the UV intensity affect this experiment? You should really be able to answer this question already, having watched this video so far. If I increase the intensity of UV light, increase its brightness, that doesn't change the frequency. It's still UV light. So the energy of a single photon is the same. However, it will increase the number of photons. Each photon has an energy above the work function, although it's the same energy as it would be for a dim beam. So if it's a one-to-one interaction and there's more photons, that means we'll get more electrons and the metal surface would lose charge at a faster rate. But because the energy of each photon hasn't changed, the energy of each electron will remain the same. Got any questions about this? Just ask. I'm going to move on from it now. This asks you to explain why the electrons are emitted with a range of kinetic energies. And this is an important fact for you to know. Why is the Ke in E equals Ke plus phi the maximum? Where does some of the kinetic energy go? We start off explaining the photoelectric effect as ever. Oh, look what it starts with again. A single photon interacts with a single electron. Energy is conserved, electrons released when the energy is greater than the work function. Now for the bit about why the range of kinetic energies. The electrons have a range of energies because when the electrons are trying to get out of the surface, there might still be other electrons or other atoms in the way, and so they collide. Think about like a mean drift velocity kind of situation, and as it's trying to shoot out of the surface, it just knocks off a atom somewhere as well. It just bounces off one and it ends up losing some of its kinetic energy in that collision there. That happens, it's just because the surface of a metal, it's not as clearly defined on a microscopic level. The UV radiation might penetrate to a few microns, and that means that there'll be atoms and electrons on top of it, and so they collide. You get it. Just learn that electrons collide with ions on their way out of the surface of the metal because they are in the way.